Life would be really simple. So we know the solution of a single electron, and we just put all other electrons, and that's it. So there will be no problem with this story. The problem sits here, right, in this two-body term. So calling it two-body because this is the mutual repulsion between the electrons. Each electrons interact with all other electrons in the story in pairs. Right? So this mutual interaction means that I'm taking actually this 1 divided by Rij, where Rij is equal to Ri vector minus Rj vector. So that's nothing unexpected, right? So this is really the mutual repulsion between electrons due to Coulomb interaction. And this is the hard part. So, but we have to sum over all possible pairs. So we pick up an electron, and that electron actually interacts with all other electrons. So then it's a sum over all possible pairs in this story. Okay, that's fine. Then we need to make only this. Calculate that and calculate that. Okay, that's the story. So how to do that? So let's try and make it by steps. So let's take the first step. Let's consider only the first step of one body. One body. Sort of term. Let's consider that. So this one body term means that we are having the psi antisymmetric, walks on Hamilton H1 and closes from the second side with antisymmetric wave function. Now we are having this square root of n from this part of the wave function. Now we have the psi h, right, according to what we had here. Psi h multiplied by the antisymmetrization operator works on h1. And from this side I have the opposite. Antisymmetrization operator multiplied by psi h exposes from here, and I have the square root of n factorial from this side. Just took this wave function. So now what we know, so this is the operator, so I can consider it with the operator of the single body Hamiltonian. So, but this operator essentially commutes with the Hamiltonian. So that's something that you can understand because Hamiltonian is invariant toward the exchange between the electrons, right? So do not change because we exchange between the electrons. If we take electron number 1 here and electron number 2 here, Hamiltonian will not change if we change the position of these two electrons. So then the electron commutes with this operator, so which means that H1 and A, the commutation relation is equal to 0. So I can exchange the position between them. So then I have in this story then the H1, then the A can go to that side, to the right to the Hamiltonian, and I have another A from here. So I have A squared operator. So the operator A squared, so A is the exchange operator. Sort of will be make the permutation. If I do, so it's also the same. So if I'm doing A square or equal, so A square is equal to A. That's essentially the statement. So it means that I don't do that much if I'm considering one permutation or two permutations. It gives the same essentially story, and I'm going to use these two facts in order to continue this calculations. So essentially, we can say that I have to consider the Hartree wave function, which is closest with this H1. And I have a single operator A, and it's called as the Hartree-Fock function. Okay, so now now we can write this guy as following. So we can write the A as in its initial form, like that. So this means that I can write that as sum over I, sum over permutations, minus 1 to the power of p, and then it will be the psi Hartree multiplied by h, so the closest between h1 multiplied by permutation. So now the point is that HI acts on a single electron. So it's a one-body Hamiltonian. So it acts on a single electron. So if it acts on a single electron, it doesn't depend actually on the permutation. So if I exchange the position of two electrons, this will not change anything from the action of this operator on this Hartree wave function. The permutation just change the position, so marks the electron number 1 with the label number 2, but the H is the same on these two electrons. So this is essentially the same thing. It doesn't matter what is the number of this electron. So it's a sum over all electrons. So if I'm taking the one, it means that inside this sum, I just exchange the position of these two electrons. It doesn't change the sign. Therefore, this actually action of this perturbation operator doesn't change anything. So I can omit it. I can throw it away. So just in this case, in case of single body operator, the single body Hamiltonian, I actually can say that everything that is still stays in the story is just the sum over all electrons, sum over all electrons I, psi h, h1, psi h. So it means that all this story of Slater determinant does not do anything if we are talking about this part of the Hamiltonian. That's fine, that's easy. This means that we can actually consider just a simple Hartree-Fock function and say that we need to calculate these expectation values which acts on a single electron wave function. So it's essential. Well, that's yeah, there is a little problem here. So because once I'm going from this line to this line, I have to change this h to h small. Because the sum is already there, so I can write this guy as the sum over I from 1 to n by small h of I. Otherwise, it's not consistent. Then here I sum over all these terms, so I have to introduce this Hamiltonian 1. But then, you know, it's just so because of the orthogonality of all this orbitals, right? We can say that this is essentially the on-diagonal elements only in this story. So we can say that this goes all sum over all these orbitals lambda. So I remind you that we consider the orbital this orbital, and this is the sum of this orbitals lambda of u lambda cube. It closes this Hamiltonian h cube, and from the other side I have this u lambda cube. That's the first part of the story. So the Hamiltonian that takes care about one body type. And so now that's the first part. So the second part will be just to consider the two body terms. That's the answer of the first body, one body term. Well, the answer, you know, something that we still have to minimize. So we will still have. So this is what gives us this expectation value of the Hamiltonian. So we'll have to look for this orbital. So we don't know this orbital yet. So we'll have to change this orbital in order to get and find this. In order to find this orbital. But let's see now. Come back to the second term of this equation, which is this two-body interaction term in all the pairs. And let's try to see. So essentially, this will be the same, right? So we will write here H2. So there is more or less a similar action up to this story. So the psi antisymmetric closes the H2. The two-body part. This gives the sum over I less than j, sum over p, all permutations, minus 1 to the power of permutation. Psi Hartree closes the 1 over Rij, that's the Hamiltonian, p, permutation, psi h. But now here there is something that will be different as compared to here. So here we just omitted the permutation. Here the permutation makes sense. There are actually two possibilities, that two permutations are meaningful. So one permutation is that does nothing. So exactly as here, right? So the permutation does nothing, so we change nothing. That will be the direct term. The second one is when this permutation actually switches between the I and J. You know, here we consider the different distance between the electrons I and J. So this electron and this electron is I, this electron J, right? If the permutation does nothing, or if the electron I remains in the same position, J remains in the same position, we get exactly the same situation as here. But there is still additional term that will survive. This additional term actually exchange between I and J. So this actually remains, so because Rij is just the modulus difference between Ri and Rj, so it doesn't matter if I take Ri minus Rj or Rj minus Ri. So therefore, this permutation is also will survive this integral, because all other permutations will bring us to the situation where the orthogonality of these orbitals will kill the terms. We have two terms in this equation. So one term will be the direct integral. I'm having here sum I less than j, and now I have this psi Hartree 1 over Rij psi Hartree. This is one I can omit the permutation operator, and the second term here minus psi h 1 over Rij multiply the permutation operator of Ij, and this is psi h. So this will be two terms, and we actually can recognize these two terms as we considered them last week in the situation of a 2-electron atom of helium. So this one was the direct integral, this was the exchange integral. So these two parts essentially remain here in this treatment, which is of course correct. So it has to be, right? So it has to be there. So this part is the direct integral. And this is what we call exchange integral. When we considered the Ilan. Right. So now let's try to push this forward. Okay, so now this can be written in a bit more direct way. So once we take this psi h with the orbital with the correct orbital, then we will have the following situation. So psi antisymmetric h2. Psi antisymmetric, this is what we have here, will be equal to 1/2 of the sum over lambda mu orbitals and u lambda multiplied by u lambda of the u I mu of uj, uj, 1 divided by rij, this is the operator that closes them. And from this part, I have essentially the same, u lambda of ui, u mu of uj. That's the, well, this is exactly the direct integral. So if you consider the direct integral that we wrote a week ago for 2 electrons on the ground state of Ilan, you will see that this is just a generalization. So it's well, we considered it actually between 2 different orbitals. So we'll see the same expression. But there we just considered only 2 orbitals. So here we sort of we sum all possible pairs of orbitals in this equation. Now there is a term. The second term is the exchange term. So 1/2 is not to take it's just because we don't want to sum over the same orbitals 2 times, right? So we don't want to. So therefore, a factor of 1/2 appears here. We have, the number of possible pairs is number n multiplied by n minus 1 divided by 2. This 1/2 comes out of this summation. So now it's sum of lambda and mu over lambda and mu, and then I have u of lambda qi u mu of qj. Now it's closest over r I j. But now from here I have u mu of qi u lambda of qj. So here we exchanged between these 2 electrons, qi and qj. We exchanged their position on these 2 different orbitals. So that corresponds exactly to exchange there that we saw a week ago. Exchange there. This is the direct. And this is the exchange one. So this essentially, it's quite a large expression, but essentially this large expression takes the same meaning that we already saw that in the previous lecture. So now we have 2 terms, the 1-body term and the 2-body term, and essentially they give some. Well, just to make a more direct analogy, we will see here like 1/2 of j minus k. If you remember, j that was the direct integral, k that was the exchange integral. Okay, so now we need to essentially take together these 2 parts. So this part plus this part, and make the procedure in order to minimize the energy. So that's the sort of a variational principle. In order to find the correct orbital, we need to go and change this orbital and see how the energy changes, and see if the energy increases or decreases. So if it decreases, so we have to continue to change this orbital until we finally find out what is the correct orbital in this string. So, but we need to do that within a restriction, which is the Lagrange multiplier. So we can take this restriction with the use of the Lagrange multiplier. So this restriction means that we have to make this minimization while keeping these orbitals orthogonal. So these orbitals has to remain orthogonal. So this is the requirement. We have to keep it. So this requirement we can write as the Lagrange addition to the minimization energy. So the energy take the energy depends on the wave function, on the antisymmetric wave function. So this energy we are going to minimize. And this energy is equal to the expectation value of one body Hamiltonian. This is what we see that there in the first part here. Then it will be added by the antisymmetric function that works on the second part. But here, in addition to that, so this is not enough. So we have to keep one while we start to change the orbitals, right? So we cannot change the orbitals as we wish. We have to keep these orbitals orthogonal to each other. So this requirement has to be present here. So in order to take this into account, we have to add this Lagrange multiplier, which is equal to sum over all these orbitals lambda, energy of the orbital lambda, and this is the orthogonal condition, orthogonality condition. That's the requirement. So this is what we have to now vary. And so we have to vary the orbital, right? Sort of the wave function, and we need to minimize this energy. So, and here we have the sum over all these orbitals. Here we have the sum over of two orbitals that acts on the operator of the 1 over Rij. So, and that's what we have to do. So now it's, you know, there are mathematical tools to do that. So these mathematical tools we will write. I will summarize this here. Then there's rules that I needed in order to do this. Essentially, what we will get out of this story will be the equation for the orbital of a single electron. But of course, because there are many electrons, there will be many equations, because each orbital will have the suitable equation for it. So at the end, we will have many coupled equations that will describe all the orbitals of all electrons. So how many is equal to n. So the number of equations will be equal to number of electrons, the number of orbitals that we want to find. Okay, so the tools. So it is that we need to. So again, that's the math tools that say how to perform this operation. So we consider this orbital lambda and orbital lambda star. These two orbitals are complex conjugate. So, and then we know that the derivative over the orbital lambda q. And so these are complex conjugate variables. So the derivative over this u lambda q of the sum over all orbitals, the integral when we integrate u star u1 over u of q1 and dq1. This will give me essentially the orbital u lambda. Because of this complex conjugation between these two variables of wave functions. Okay, that's the tool number 1. The tool number 2 will be just that here, this is just the multiplication between these two orbitals. That now we want to have, that's for this part, right? Of this energy functional. And for this part of the energy functional, we have this Hamiltonian inside. Therefore, we need to use the variational tool of u lambda is over the sum over all orbitals nu, the integral over u u1. Well, q1 means that it can be q high, any now it's the Hamiltonian u1 and u of q1. q1 dq1. So this operation will give me Newtonian q acts on u lambda of q. This part will act on that. Sorry. So what we have in the at the end is this story that has to be treated as well, right? So here we have the third two, the variation over u lambda star over u over sum of mu the integral over u mu star u1 u mu star of u2. This should be closed with rij, well 1 2 essentially, not ij, but 1 2 because here orbital, so the coordinate of 1 of the electron 1, coordinate of the electron 2, so it's r1 2, and now I have this u lambda of q1, u mu of q2. So the integral should be taken over q1 and dq2. So this will give me the sum twice sum over dq of the integral, sum over mu of the integral of the integral of mu of u mu of q2, 1 over r12 u mu over q2. This is multiplied by u lambda over q. So if you just look at this expression and recognize in this expression something that will take the direct integral, because here there are the same orbitals here in this integral, which acts, so this actually gives a certain effective potential on the orbital lambda. And this is this part of the story. So there's still another part in the story, so the fourth one, the last one. So this is the first thing that we need to do, which will be the du lambda star of u that acts on sum over mu dq. Well, we'll write that. So here the integral is missing the integral, so the integration of the dq2. Here I will write the terms of mu star of q1 and u mu star of q2, 1 over r12, u of mu q1, u of mu q2. So this should be the integral should be taken over q1 and q2. So this will be equal to the sum over mu twice. Again, here we have the integral in this story of mu star of q2, 1 over r12, and here it's in mu lambda over q2, and this should be multiplied over the wave function u.
On the third row, it's supposed to be not lambda, right? It's
What?
supposed to be mu. On the third row,
Say it again.
on the third equation, it's supposed to be not u lambda. Third one, not third.
Here?
No. One above?
Here.
Left. Left,
Here.
no, it's fine. Left.
That's supposed to be, well,
Here, where your finger is.
Yeah.
Left.
And then this has to be, instead of lambda, it should be,
No, this one shouldn't be lambda. This one should be mu.
Inside the integral.
The inside integral should
oh,
be
the
mu.
mu should be here. No, but I'm saying over
on the
mu.
left part. This should be mu.
So here I'm summing over all orbitals mu. It's mu inside, the same orbital. And I'm summing over all mu.
בתוך האינטגרל היבש של חלק כמעט זה בדיוק.
Oh, okay. So I have to have here, yeah, let's check again from where I missed the story. So it's here, in a second. Yeah. So that's sort of the tools that we need in order to make the variations of this energy functional. And therefore, after applying all these tools and variations, we should end up with the equation that describes the orbitals. So then the Hartree-Fock equation that we get after performing the minimization of this energy functional, and we are ending up with the Hartree-Fock equation for the orbital. So the H, the small Hamiltonian, single body Hamiltonian, acts on orbital u lambda of u. That's the single part. Then we have more part of two-body directions, which should sum over all orbitals. Mu of q right. So that's just a second. That should be. Yeah, we have to take two different electrons in the story. So it's u of mu of q of 1 over r, which actually connects this. So the electrons R1, R2, that could be closing with u mu of q, and this is the that is multiplied by the same orbital u lambda of q minus the sum over mu orbital of mu cubed q 1 over r12 u over lambda of q, and here I have the u. And that should be equal to the energy of this orbital lambda. So it's easier, of course, to think about, so this q is a sort of coordinates that includes the spatial coordinate and the spin coordinate, so it's easier to write this equation once we consider the orbital lambda of q equal to lambda of r, the spatial coordinate, multiplied by the spin coordinate of psi of ms lambda, of the orbital lambda. Right? So this is something that we actually can consider here, because this will give more sense to the equation. Otherwise, it's too. So this q is too is not really clear. It has to be separated back into spin and spatial orbitals in order to see what this equation actually gives. Right? So it's can be written, right? So this is a small Hamiltonian. So this small Hamiltonian means that this is a single part, single Hamiltonian, single particle part of the Hamiltonian. So it's minus 1/2 Laplacian squared that acts on spatial coordinate r minus z divided by r. This is the part that is written by small h, which acts on the part on the orbital u lambda of r. Now, plus sum over mu, which is not equal to lambda, integral over spatial coordinates of u mu star of r prime, u mu of r prime divided by r minus r prime. That's the integral that should be taken over r prime. And this provides a spatial sort of potential on the orbital u lambda of r. So all this acts on the orbital u lambda as well. So this part we know very well. So this part is a new guy in the story, and this is not the only one. So there is another part, right? Which is, this is the direct integral, and this is the exchange integral, comes from here. So here we have to have a summation over mu not equal to lambda. So, but here we have this delta function that makes the spin of the orbital lambda and orbital mu. So it's zeros up quite many terms. Only if we have the same spin. in order to take indeed indistinguishable particles, in order to exchange between them. And then we have here the mu of r prime multiplied by u lambda over r prime divided by r minus r prime. So the integral over that dr prime. So this work on the orbital u over r. This is equal to e lambda u lambda of r. So these are this is sort of an equation. So it's not an equation. There are many equations here. So it's, because all these equations are for each orbital. So we have, say, n equal to some number. So n equal to 100, you know, but as many electrons as you have. But this equation describes only a certain orbital lambda, a certain electron. So and here you see that this orbital is affected now by all other electrons, because here you have to sum over all other orbitals where the electrons are. So this is sort of something that has almost no way to solve, right? Because in order to find this orbital, you have to know what this orbital means, right? So these orbitals are the orbitals of other electrons that act on the orbital that you want to find. So you are sort of locked here, right, in this story, because in order to find this orbital, you have to know what are all other orbitals. So these equations are sort of, you know, you see that this is a differential integral equations to find all these orbitals, and they're essentially so I have to write hundreds of equations for one orbital, but each equation depends on other orbitals, so they are coupled. So I have a system of as many electrons, a system of equations, as many electrons as you have, which are all coupled together. So the only way to solve these equations is to go in self-consistent way, so an iterative way, which means that you actually assume what are all these orbitals at the initial moment of time, and then you plug in these orbitals inside here in order to find the new orbital u lambda, right? And then you find this u lambda, knowing that this, using known initial guess of the orbitals, and then you should find this new orbital and plug it back into the equation for this orbital back into other equations, right? And then solve the other equation with new orbital, and then when you solve all this equation with new orbital, then you arrive to new orbitals, all other new orbitals. Then you can plug back these new orbitals into this integral and solve again for finding new orbital here, right? And hope. So what you really hope to have here, that this procedure will converge. If this procedure do not converge, this is a problem, right? So this means that, you know, changing the orbital by the first iteration, you hope that the next iteration, the change will be smaller, and the next iteration will be even smaller, and the next iteration will be even smaller again, and then this convergence will bring you at the end that you just solve all this equation and you find the orbitals, and these orbitals will not change anymore after you solve it again and again and again. So then you arrive at this solution, which is the minimal energy solution. So you change the orbitals, and by changing the orbitals, you find the minimal energy. Once you arrive into the minimal energy, you stop changing the orbitals, so the orbitals stay constant. So that's how this machinery works in the Hartree-Fock approach. Okay. So now the surprise is that you are going to have that in the next homework to solve this story. So of course, I'm giving you the easiest part, the most easy part to do in the whole story. This is a complex, you know, it's especially complex if you take more than 2 electrons, right? So it becomes very, very complex stuff. And this is not what I'm expecting from you to do. So I'm expecting from you I'm suggesting you to do in the next. So you have to solve. By the way, I already uploaded, right, the new homework, right? For you, it's already. If you don't know, so there is a homework for you to return in 2 weeks. So that will be the next one. So in this homework, you will be asked to apply the Hartree-Fock method in order to find the ground state of helium. So that will release you from the prison. Right? So remember that we are making sort of different approaches which are better and better and better. This one should be the best approach that will allow you to come to the ground state of helium atom and to get it as close to the experimental value as any numerical method can do. It's actually this in the case of helium, this method gives you really good approach, a really good understanding, a really good answer, so you really get it equal to the experimental value. So this approach works. So it's a self-consistent method. So it's really gives you this part, gives you some very interesting understanding that you just consider this is the mean field. This is the mean field part, right? So what does this mean field part means? It means that this orbital fills all the other orbitals. So all other orbitals apply some potential on this orbital that you are looking at. So this means that a single electron actually flies inside a certain mean field that produced by all other electrons. All other electrons creates a potential for this electron. So we can consider this as a certain potential. And here, this is the potential produced by the nucleus, and this potential is produced by all other electrons. So and this is as well, right? But if you will see quite immediately that this term drops away if you consider the ground state. So that's exactly what happened also a week ago, right? So a week ago, we saw that the only term that contributes to the ground state is this one. This term appeared only once we considered the combination of 2 electrons, one on the ground state, one on the excited state. So that was where this term was non-zero. Right. So that's what you you will see how it works. So you will see essentially how good the method works. So how fast the convergence occurs. So it's everything that you will be able to see once you realize something. It's not for this. It's not a very easy task, but it's not a very complicated task either. So you can do that, and it gives you some real understanding how strong the method is. It's really strong. Let's see just a little bit about that. What we saw here, just a little bit more. So the Hartree-Fock equation we can actually see from here, right, that it's not anymore on the board. Yes, it is. So it's here, right? So the expectation value of the two term is equal to 1/2 of j minus k. Okay? So the direct integral and the exchange integral that we see here. But if we look at the final term that we have here in the Hartree-Fock equation, so we will see that essentially there is a difference in the energy. So if we take now, so if I'm having the expectation value of, I will write it here, so the expectation value of the Hamiltonian closest between this full wave function, and this time the expectation value of the Hamiltonian is the full Hamiltonian, is H1, one body and two body Hamiltonians. So this guy will give us the sum over energy levels. So energies of E lambda. So it's sum over E lambda. Sorry. E lambda over lambda plus part of this part, right? So 1/2 of j minus k. So if we have a look at the energy here, sum over all energies. So right, so this is not very good to write it like sum. This is actually the sum over all energies. So this one is the sum over single body terms. Not here anymore. Write it like H lambda. Some energy just related to a single body part of the Hamiltonian. So this part. And now if we look here, what's going on? So here we have this integral, which is the direct integral. And here this is the exchange one. So now if I take the energy of this string, so this will be the sum over lambda E lambda equal to this, the same term like I have here, from a single term over all orbitals lambda, plus a direct integral, which is the j minus k. So you see the difference between these two cases. So if I calculate it from here, so I have this 1/2 here, but at the end, when I get the Hartree-Fock expression, so the energy is essentially here is different by the 1/2. So it's not a mistake. So it's essentially something that is related to the total energy and the meaning of this energy E lambda. So E lambda here, that you see here, is not the total energy. Okay, so it's not the total energy. It's a difference. So it can be written like sum of. So it's a sum of E lambda over all orbitals lambda equal to expectation value of H1 plus 2 times the expectation value of H2. Because the expectation value of H2 was 1/2 j minus k. Here it's 1, so we have to write it 2 times. So if I write therefore the total energy will be equal to over the sum over all E lambda minus the expectation value of H over all lambda. So the total energy of the system is not the sum over all the energy of all orbitals. Total energy is less than total energy of all orbitals by this expectation value of H2. So the meaning of E lambda, so this is essentially exactly the exchange energy that reduces the total energy in the story. So the meaning of E lambda is essentially how much energy should I introduce into the system, how much energy should I apply into the system in order to remove the electron from this orbital. Okay. So this is more like a chemical potential. If you know feel the differences now between the chemical potential and the energy. So the chemical potential is the energy per particle. So here, this is more like a chemical potential. So this is the energy per orbital. So in order to, this is how much energy it costs to put this additional electron from this into this orbital. Okay. So it's not the total energy of the system. The total energy of the system is less than that. Okay, so that's just some additional information that they want to tell about the story. And now we can try to now say something about, it's sort of by side to tell you about that, so you will probably not appreciate that much, but I still will tell you about this just by a side note. Okay, so it would be like a side note about the Hartree-Fock equations, but in the case of bosons. So it's imagine that all electrons are not fermions but bosons. So what then you will do? So what we will get? So we will get a much easier situation. We'll give a different equation. So just again, this is a side note. So just in case, instead of considering this equation for fermions, let's consider that for bosons. So we are considering the bosons instead of fermions. It's not correct for atom, right? So because in atom there are electrons, so they are fermions. So we cannot apply this for a bunch of electrons. But if you have a situation where instead of fermions you have a boson, so then you can also still apply Hartree-Fock theory, and in this situation, so the ground state of Hartree-Fock ground state will be just the wave function of R1 red Rn. So this wave function can be written, so it's not anymore on the blackboard, on the whiteboard, but you will see here, so that this is just can be written as a separable wave function, right, as we did before. Phi of Rn. So that's the multiplication of all this. I don't need right here to play with anti-symmetrization of the wave function. So I don't need to apply here this later determinant. This function is already symmetrized, so I'm dealing with bosons, so that's fine. I don't need to do anything. So the direct interaction term here in this story can be written relatively easy. So the direct interaction in Hartree-Fock representation, that's the direct term. So it will be just sum over all orbitals, the integral over all space, dr prime, v of r minus r prime, modulus of that, phi of r to the second power. So that's now in order to try to so okay. First of all, we can consider, so if it's a ground state that we consider here, if this is a ground state, so we can say that all orbitals are the same. So we can just write here just the multiplication of the number of bosons that we have in the system, multiplied by the whole integral with the space with this potential, r minus r prime potential, and p of r to the second power. So now, now in order to take this integral, we have to know what is the potential of the interaction. The interaction potential is essential. So I cannot take the interaction potential as a Coulomb potential because it's nonsense, right? So Coulomb potential works between the electrons are fermions. But I can so tell you that we can find a situation where this potential is extremely easy. So that's something that I'm going to tell to those of you who will survive the first part of this course and will still taking the second part of this course will be the next semester. So the first, this potential is in case of atoms, for example. So atoms can be bosons or fermions. So in case of atom, as the whole system, right? So not the electrons inside the atom, but I'm considering the atom as a whole and the external degrees of freedom that where it will walk. So this potential can be considered as a delta function potential. So it's a contact, essentially as a contact potential. So it's very different from Coulomb potential. Coulomb potential is very long range. So here I actually can consider the potential which is the delta function. So this potential is very short range, extremely short range, zero range. So this potential can be written as a delta function. So we sum a value, characteristic value, and this is just the delta function of potential. So in this case, this integral is extremely simple, and I'm getting that the interaction VD, the interaction potential, will be equal to n multiplied by g multiplied by p of r squared. So therefore, so exchange interaction doesn't exist, so it's a ground state. So this part doesn't exist. Boom, boom. And this part, all this part, well, you know, essentially not. There is no this term in this part because the potential is different. But all this part reduces essentially to this additional potential. So the big function, so the equation that I'm having in this equation is just the kinetic term minus h bar squared divided by 2m Laplacian, which acts on the wave function, plus this interaction, right? So this interaction is just equal to gn psi p of r squared, and all this story acts on the wave function phi. So now I have to find the energy level of this type of interaction. So now it's really, so this equation is well known under the name of Gross-Pitayevsky equation. This is known like Gross-Pitayevsky equation. And this equation describes the behavior of Bose-Einstein condensation in atoms. That you know that describes how the wave function of this Bose-Einstein condensation behaves. So that's very simple. But essentially, it comes from the same Hartree-Fock theory. It's much easier to do because we are considering only the ground state, and we are considering delta function potential, and we are considering bosons, right? So it reduces the problem to almost trivial, but this comes from the same consideration of Hartree-Fock, and we get boil down this theory to a well-known equation that actually describes the real situation. So it describes the real situation of bosons inside which interact with each other by collisions. Something that we will see. So if you want, this is something that this you will see next semester. Those of you who want. This is what we are going to talk about so it's easier than what we are doing now. Something that probably you should take into account. But this is the easiest part. Okay, anyway, so let's come back to, this is the by-side effect, so side note, it's not the part of the course. So now we can actually, probably the good thing to do is just to make a certain overview of many electron atoms. I'm not sure I will be able to do that everything today, or maybe yes. But I will try to sort of take an overview of many electron atoms. So many electron atoms is not a simple system. So you can see, you can just test like this by considering this just only a simplest part of that, because this simplest part considers the Coulomb interactions, does not include the interaction between spins, and it already brings us to heavy numerical calculations in order to try to estimate the energy levels of the system. So it's very well known that we know analytically hydrogen atom. People says that they know almost analytically helium atom. So almost analytically means that there is no analytical solution. But numerical solution is so good that we can describe this almost as well as analytical, which is sort of nonsense. But whatever, still, I would say that if numerical values that you get out of the theory comparable with the experimental uncertainty, then you can say that the theory is indeed as analytical as it can be, right? So it's better than the uncertainty of the experimental measure. So helium known this quite well, so it's a relatively easy problem. But any other atom is in no way can be considered as analytically known. So it's heavily numerically based calculations, and they are less exact if you go to heavier and heavier and heavier atoms. So you have to take into account more and more and more and more corrections. And imagine why it's so, because electrons also attract stronger to nucleus, so it starts to be more relativistic. So all relativistic corrections become complex, more complex to take into account. So it's quite fast becomes clear that Hartree-Fock method is not the solution for everything. So it can give you a good solution for relatively light atoms, but it's not a good approximation for heavier atoms. So there are different theories for that. If you want to calculate the orbital motion of the electrons, but what we want to say is essentially, try to sort of get some intuition about some numbers that we can see out of the story. Remember that atomic physics is already 100 years old. People developed a lot of efforts, numerical as well, in order to build up knowledge about the binding energies of many atoms. So they are quite good. So if you, for example, pick up some atom out of the table of elements and you try to find the energy levels by spectroscopy, so you will find them. So it's the combined effort. That was a combined effort of experimental measurements with the theoretical calculations. So some of theoretical calculations cannot be performed without the input from the experiment. But nowadays you can really sort of see. If you go to web page of NIST, of National Institute of Standards and Technology in the United States, they have a huge database about atoms, and you can really extract energy levels of almost any atom, even if it's as crazy, it can be found in the different places of Mendeleev tables. You will see them, and the predictions are quite well. So at least you can go there and look for this energy levels, and you will most probably find them. So this is a great, of course, success. Like you know, it's not as big as cataloging all genome of the whole humanities, but it was a huge work. So you know, for many people. Now we will try to make sense a little bit for a few numbers that we can tabulate. Essentially, what I want to tell about is the ionization energy. This is something that relatively easy can be, let's say, understood. So I can remove that, and we will try to see. So let's try to make a small table that will take that will describe us sort of a round state of different atoms. So we'll go along the Mendeleev table and try to see what sense we can extract out of there. So we use so-called russel-saunders notations. Russell, it's new year, russel-saunders notations, which gives a certain spectroscopic notation for orbitals. So it actually goes like L, it's the orbital angular momentum. Here it's noted like J, this is the orbital plus a spin of electron angular momentum. And here we have 2s plus 1. So S, L, and J, they are the sum of all electrons. So this is the sort of, you know, a common notation in spectroscopy. So we will start by writing, so we have a name of atom here, and then we will see this orbital, you know, the field orbital, where are full orbitals, electronic orbitals. And here we will have the ground state injection, and we will see the ionization energy. So if we start with hydrogen atom. So that's the hydrogen. So hydrogen atom has one electron. The electronic orbital of this will be called 1s. This is s orbital, the ground state. Right? So the ground state in the russel-saunders notations will be called like s, because we are on the ground state. So L is equal to 0. It's always s orbital. So J will be equal to 1/2 because we have A equal S. It's 1/2. And here we have the 2s plus 1, so it will be equal to 2 because s is equal to 1/2, so we have here 2. So the ionization energy you know. So the ionization energy of this hydrogen atom you should know well now, even if you didn't. Right, so it's 13.6 electron volt. This is what is the energy that it takes to extract the electron out of the atom. Out of the this is exactly the Coulomb interaction potential and how much energy it takes to extract it out. So now let's go to helium atom. So helium atom and the electronic orbital. So we have on the ground state 2 electrons. So the electronic orbital will be called like 1s2 because we have 2 electrons, 1s, one spin up, one spin down. So it's a single state. And the ground state in the russel-saunders notations will be sort of noted as s orbital because L is equal to 0, but J now is actually 0. It's the L plus S1 plus S2. So, and S1, S2 has opposite signs, so we have here the 0 and J equal to 0. And but S is equal to 1 here. Because S is equal to 0, so I have to write only 1. It's less in the story. So what is the ionization potential here? So the ionization potential here is actually something that we talked about last week. You will see it as well by doing homework, the next homework, not this one. So in this one, you won't see that. In the next one, you will derive this number. Well, you will derive the binding energy of the 2 electrons, and then if you have the free electrons and then minus the binding energy of 2 electrons, you'll see this value. You will be able to extract this value. So that's the exact value of ionization energy. So this ionization energy is equal to how much energy you should apply in order to extract 1 electron out of the story. So not 2. So only 1 electron. That's the meaning. Usually, the meaning of ionization energy is how much energy you should apply in order to extract 1 electron. So you take the helium atom, which is neutral, extract 1 electron. It's become a helium plus 1, plus 1. So only 1 electron is removed. So this is much deeper bound system. This is something that I also already mentioned last day. It's much deeper bound system, but it's, of course, you know, the binding energy here, you know that it goes the potential, it goes like Z divided by R, and we know that the energy goes like a Z squared divided by N squared. So the N is equal to 1, so it's always ground state. But Z goes into the second power, so it's Z squared. So in helium, Z is equal to 4, right? So and if I'm taking it straight forward here, so it's 13.6 multiplied by 4, I'm getting 54 something, right? It's significantly larger than this value, right? So I cannot, of course, this ionization energy is less than what I calculate directly by applying the scaling rule from hydrogen atom. The reason for that is, of course, you understand it quite well now, comes from the repulsion between the electrons. So two electrons has repulsion, has energy of interaction. This energy of interaction energy reduces this binding energy by some quite large amount, so about by a factor of 2. So now it's interesting to go to the next story in the system. So if you remember by heart the table of elements of Mendeleev, so you will know what is the next one in the story. What?
Lithium.
Lithium, right. So absolutely right, it's lithium. This is the alkali atoms, so it's a hydrogen-like system. So they have 3 electrons, right? The lithium atom has 3 electrons. So the system has one, if I'm writing the electronic orbital, it's 1s2. So 2 electrons on the orbital, on the s orbital, cross s orbital. But the last electron cannot sit on this orbital because of Pauli exclusion principle, so it has to occupy the next one. So the next one will be the 2s. 2s electron is the electron that sits on the next orbital. So remind you the picture. So we have here the energy. So this is the n equal to 1 energy level. This is the ground state. So this is 1s orbital, and it has. If we forget about everything that we know about the hydrogen atom, especially forget about the hyperfine splitting, so that will be the only energy level with angular momentum L equal to 0. But now, so we can put here only 2 electrons. Now the n equal to 2, right, this will be already 4 energy levels. This one is the s orbital, this is the s orbital, and this one is the p orbital. So this p orbital, so then putting these 2 electrons allows me to go only to there, right? So to that orbital. Look how the picture of hydrogen atoms affects us, right? Of the whole story of atomic physics. So essentially, we don't change this picture. So we keep the same orbitals. They're very different, these orbitals, from how they look like. This you will see once you calculate the true orbital of the helium atom. You can compare that. You know, I'm just telling you that the initial guess of the orbital that you will start with will be, of course, hydrogenic orbital. And then you will see how this true orbital is different from the hydrogenic orbital. But still, we are talking about the same sort of construction, right? So principal quantum number orbitals, the electrons are going around with the same orbitals. And this is, of course, the consequence of a strong central potential character of the system. So the system remains central potential mainly, and all deviation from central potential can be treated by perturbative. They are small. They are extremely important because I remind you the key word of the course is the precision. Of course, if you want to go and precisely describe all energy levels of the system, so you have to make much harder calculations and include all the corrections, including relativistic and spin corrections, degrees of freedom, in order to see how all energy levels behave. But the gross structure remains the same. Yeah? Even if we are talking about many electron atoms, well, then it will be the n equal to 3, and so on and so forth. So we actually quite automatically put electrons on certain orbitals here. And we imagine that they keep enjoying the general picture that we've got studying hydrogen atom. Okay, so lithium, right, provide us with an interesting example. So, which is probably the best example that can go with this, the closest to this simple scaling factor that we can extract from the lithium atom. Right, so what is lithium atom? Lithium atom has 2 electrons here on the close orbital to the nucleus, and then there's the third electron which is farther away, right? So it occupies the next first excited state. So this means that we can actually remember what we said before, that there is a screening effect, right? So we can think about this electron on the excited orbital like an electron that sees, instead of the full charge of the nucleus, which is equal to 3, we can actually imagine that it's very far away, and it's actually what it sees sort of a screen potential with 2 electrons that screens the Coulomb potential of the proton. So what we have is essentially a hydrogen-like system with a single electron. We just connect it to a single proton, but it's farther away, right? So what does this mean? This means that if I'm going to calculate this ionization potential, I have to take into account this 13.6 electron volt. It's a single, right? So now I'm talking about a single electron on the excited orbital, but I have to take into account that this n is equal to 2 now instead of 1. And if you remember, the energy goes like a 1 over n squared. So therefore, I'm on the position of taking this 13.6 divided by 4, and this is the prediction of the ionization energy for lithium atom. Okay, so do you follow me? So the single prediction will be just here, 13.6 divided by 4, which is equal to 3.4 electron volt. This is sort of something that I would expect from naive consideration based on screening argument, right? So the true number is more than that. So it's 5.39 electron volt. But it's deep drop, right? You see that if you are going to draw certain curvature of how the ionization energy behaves as a function of atomic number. So you see that here I'm going up, sharp up, whoops. I come to the atom. So the helium atom is the first element in this gases, noble gases, right? So these noble gases that are characterized by the full orbital, right? So once we fill the orbital completely, we arrive with this noble gas. So these noble gases are characterized by high ionization energy, always. And then the next step in the left table will be the alkali atom. And the alkali atom has only single element, it's a single electron in the next orbital, and it was always characterized as dropping down in the ionization potential. And interestingly, this is actually the less ionization potential that we can find in the table, in the Mendeleev table. So you see that the difference is, yeah, it's not negligible. So this means that we cannot really say that our consideration of screening to be perfect, you know, like working as a perfect screen, right? So, but this, which is not very unexpected, by the way, because this is still s orbital, right? So this is s orbital. If you remember, the s orbital is the maximum on the nucleus. So the wave function has the maximum on nucleus. So the electron is not. It has a very long tail because the tail here drops significantly slower than the tail here on the ground state. but it still has the maximum at the nucleus. Therefore, the difference here is significant. So it's significantly better attached to the nucleus than just a simple consideration of scale. Well, this is something that fits well with the image that we have from a hydrogen atom and from understanding how the wave functions look like if we consider different orbitals. Okay? These are still a hydrogenic wave function that we consider. Okay, now we can get a bit further with this simple exercise. So we can go next. Next will be the beryllium. So beryllium is Z equal to 4. So I'm going to Z here. See that 1, 2, 3, 4. So now I have these 2 electrons sitting on S orbital and 2 other electrons sitting on 2s orbital. I fill the 2s orbital and I again have just here the russel-saunders notations. So it's S, it's still S orbital. 1/2. This is for lithium. For beryllium, I will have S0, 1, and the ionization energy will be larger. It will be 932 electron volts. So this, yeah, okay. Of course, this is something that we will expect because the Z goes up. So it shrinks essentially the size of the atom. Mm-hmm. So the size of the atom, right? Probably hear about that. So I don't know if we will have time, probably not, to talk about another popular model of an atom that was very popular in the 30s. It was developed by Enrico Fermi in Italy. And it's called the Thomas Fermi model. This Thomas Fermi model actually, is simpler, significantly simpler. It's still mean field model. So it's also something that considers the C of the electrons as a C that creates a potential on a certain electron. But it's significantly simpler than Hartree-Fock method. So Hartree-Fock method is, but it's less exact. Well, it gives you significantly less information than Hartree-Fock. But it gives a very interesting information about the size of the atom. What is the size of the atom? Right? So if you take the hydrogen atom, you know exactly what the size is, right? The electron in the ground state, so it has the size which is equal to Bohr radius. But now, what is the size of the atom which has hundreds of electrons? It looks like significantly larger, right? So it should be like some kind of balloon as compared to the hydrogen atom, right? It seems to be something huge. Do you agree? Based on, several hours that we spent together, you should already feel that this is not the case, right? So why it's not the case? It's not the case because we put more protons, right? So it's not only putting more electrons in the story. If you put only more electrons in the story, you will not get bound system. By the way, hydrogen minus, it's hydrogen with 2 electrons, like a helium-like system. It's a helium-like system, 3-body system. It has 1 proton and 2 electrons. Is it bound or not? Good question. Well, the good answer for that, it's bound, but just. It's really a just bound system. It has 1 bound energy. So it can be kept together. So 1 proton can keep 2 electrons. This is amazing, right? This is really amazing. It's still a bound system, but this system, the idea why it's bound is that the electron is smeared on the large space around the proton, right? So that's the reason. So the electrons can be really far away from each other, and they feel repulsion less than the attraction to even single proton. But then the system is large, and there is only one ground state. There is no excited states. So all excited states aren't bound. So only one single ground state are bound in the system. So this is a large system. And then we go to a larger atoms, right? So larger atoms means that the larger atomic number. So it's 4, 5, 6, 7. The proton becomes really strong in the force to attract electrons. So we put more protons in the story. So the atom shrinks, okay? So all the electrons actually packed inside this more or less the same volume. So the amazing fact after the result, the amazing result of this Thomas Fermi theory, or the amazing results of the Hartree-Fock theory that you will see yourself. You will see how the orbital looks like of the electron as compared to a hydrogen case. You will see that the electrons actually packed very compactly inside this structure, and the size of the atom remains a Bohr radius. So if you say a Bohr radius as a characteristic size of the atom, this will be the right guess or right answer for whatever atom you take. So even the largest atoms with hundreds of electrons, somewhere close to 200 electrons, it stops to be stable. The system stops to be stable because of very different reasons. So there are different reasons, right? Why we don't have atoms with 500 electrons? This is another very amazing question.
The nucleus becomes unstable.
Well, so actually there are two different reasons. So there is instability in the nucleus. So you cannot, at certain point, the nucleus becomes unstable. But it's also, it boils down to the question of instability and in the number of electrons that we can put into the system, even if the nucleus will be stable. So it's a different type of instability which is related to relativistic effect. So because you packed more and more and more and more, so you come closer and closer to the nucleus, you become faster, 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 faster. You get closer to the speed of light. So the electrons becomes really relativistic, and they develop the relativistic instability. So it's a very interesting question, which is far beyond what we study in this course, but it's something that was considered significantly in the literature in 60s and 70s, just to study different relativistic effects. So there are two different types of instabilities that creates the upper bound of the largest atoms that we can have. But the interesting stuff is that these atoms, or all atoms that are stable, they are essentially the largest. They are essentially of the size of the Bohr radius. Well, few times Bohr radius. Okay? So 4 or 5 times Bohr radius. Okay, the largest one. But interesting, by the way, that only a couple of years ago, I just saw a paper published about the heaviest atom of the table of Mendeleev, which essentially resembles a soup of electrons with protons. So it can be actually considered a real soup that mixes together all of them. So they are so heavy that they are very close, and the nucleus is very high. And this atom, the largest, which is still stable, is very little resembles this nice picture of orbitals of electrons and so on and so forth. It looks more like a soup. So this is what the claim of this. So it's really more like a Thomas Fermi model that really considers them like a soup of electrons. So and that's the end of the story. So once you have this strange soup of this, you know, right. So this is yeah. What is the name of this plasma? Right. So it looks like more like a plasma because the plasma is the mixture of the positive and negative charge elements that are not together. Okay. But this is very compact plasma, which still keeps. So plasma usually do not have a bound state. So this is why it's not plasma. It's still bound, but do not really resembles the familiar picture that we usually consider as orbitals of elements. Okay, so anyway, that's just the mark side. So if we go further, we can say that next one would be the boron atom. Boron atom is 5. It has 1s2, 2s2, and 1p electron. So the 5th electron goes to the p orbital. And then it starts to be called like a p, because the L is equal to 1 now for the last for the ground state, right? So the systems. And it has 1/2, and it has here 2. It has a less essentially, right? So because this is the additional electron, which is farther away, right, from the nucleus. So the ionization energy is expected to be smaller, and it is smaller. It's 8.3 electron volt. And this is something that is really goes together with our understanding that we already developed looking at the structure of the atoms. So it goes more like further filling up different orbitals. So we can say that, for example, if you go toward the end of the second row of the Mendeleev table, we will have here 10. So that's the atomic number of neon. Neon is the second noble gas below helium. So this neon has a fully packed electronic system that 2 electrons here, 2 here, 2 here, 2 here, 2 here, right? So that's why it's 10. So we have here 1s2, 2s2, and 10 and 6p. Sorry, 2p6. So this is 2p. This is 2p, 6 electrons on that. And it will have this still simple Saunders, russel-saunders notation of S, because the p orbital is fully packed, so the orbital angular momentum is equal to 0 in this situation. J is also equal to 0, and S equal to 1, so it's like helium, right? So it gives you the same notation as helium atom. This is the same. You can consider that this is also similar between the hydrogen and lithium atom. So they have this russel-saunders notations. They pick up more or less the periodicity of the Mendeleev table. So the ionization energy will be the deepest one, right, in this line, but not the deepest one in the whole table. So it comes closer to the helium atom, but it's do not reach it. So it's 21 0.56. So there are more elements here, more elements here, more elements here, right? So that this is the binding energy of the neon atom. So the binding energy is less than the helium, and as I told you, the helium is the champion. So this is the deepest bound system from the atoms. Neon comes closer, and then after that you have sodium. Sodium is the 11, the element 11, so it's 1 electron up again. So we fill with the electrons this first orbital, the second excited state. It goes to the third excited state, to the s orbital. So it's helium-like system, sorry, hydrogen-like system, which has even less, scaling factor. So the scaling factor will tell us 13.6 divided by 9. So it's really weakly, should be weakly bound system. But the ionization energy of sodium is so 11 sodium. It has this. So 1s2. I will tell that as. So this is the neon plus 3s electron, 3s electron, 1 electron on the principal quantum number 3. And now we get this mutation like S2 1/2, and we get the binding energy here will be just 5.14 electron volts, which is not that far from the binding energy of lithium. So here it's further and further away. So the system is not, according to this binding energy, you can understand easily that the size of the system is nearly the same. So it's essentially, because this binding energy is even larger, so this binding energy is even, it's nearly the same, right? So it's nearly the same binding energy. So it's a bit larger, sodium atom, it's a bit larger than lithium atom, but only a bit, right? By 10%, something like that, even less. So you will see that I put more electrons, but from the point of view of the size of the electron, of atom, you see that the size of the atom do not really change, right? So and this is, it starts to be further and further away from this simple scaling relation, because simple scaling relation gives you indeed very weak binding energy, more weak, if there is a full screen. But full screen is not the correct way to see the system. Okay, so then there is more elements. So if you go to argon, you get back to deep binding energy. Deep binding energy gives you something about gives it something about 15 electron volts. Then we come back to Picasso and so on and so forth. So it's become more and more complex, the story, because it's not going to be as simple as that. So here is 1, 2, 1, 2, 1, 2, 1, 2, 1, 2. Or it was 1, 2, 1, 2, 1, 1, 1, and then 1, 1, 1. And then we filled it with all electrons. Then it becomes more complex, right? So it's not really starts to be, so here, for example, S and P electrons I feel, but there is a d orbital, and this d orbital, not necessarily to go for the d orbital from n equal to 3, I can actually go, it can be less costly to go to the next excited state, n equal to 4 s orbital, than to feel first the d orbital. So this construction becomes more complex from the point of view where the electrons is found, and just can probably sort of giving some idea about the ionization energies of the system. So here we have ionization energy. Ionization energy. So we know that the hydrogen atom, so here it's 5, 10, 15, 20, 10, 15, 20, 25. So the hydrogen is somewhere here, right? So that's the hydrogen. This is somewhere here. And then the helium atom goes up. Right? Goes up to here. And it drops down to lithium atom, which is all the way down to here. So and then all the atoms start sort of doing some zigzagging, coming back to argon. Argon is about here. This is the argon. This is lithium.
Why is
Well,
that?
there is a little zigzagging that you can see. Why is that?
Why is that? Why do we get the zigzagging, not the
Well,
linear
that's
approach?
what you see here, right? So you had here larger value, 932, and the next one was less.
What
Oh.
is the physical explanation of that?
That's what we saw here. That if you look at the description of the electrons, so here, for example, if you look at the helium has 2 electrons on s orbital down and 2 electrons on the highly excited state. So here you have, and these 2 electrons, right? The 4 electrons occupy s orbital, and we know that s orbital is quite well bound to the nucleus because the character of the s orbital goes up. Here, in the next one, you know that you fill, so the next position that you can fill will be the p orbital. So the electron will be on the p orbital. So p orbital has less interaction with the, so indeed you get more protons in your nucleus. So you sort of pack your system closer. That the electron that you put on the p orbital has less, occupies significantly larger volume and has less overlap. So it's a 0 overlap with the proton. Therefore, this energy to extract this electron will be even less than extracting the s orbital or electron. That was the hand-waving explanation. This is why you see here, each time you see here dropping a little bit, means that you actually occupy some p orbital, d orbital, some orbital that becomes less attractive than the orbital that was captured before. Okay, so then and then it goes sort of down. Potassium atom. Potassium atom is even less bound than lithium by a little bit, by some amount, and then you get some, more zigzagging even better. It goes up here again to fit the Nobel. Probably. Well, it's not a potassium, it's sodium. Nobody stopped me. It's sodium.
Is it argon or neon? The one before.
The next one, well, it's not the argon, it's the neon, right? So I just looked at the next stage already. So from sodium, it goes like more like regular structure to argon. That's the argon. And then it goes down to potassium. So the potassium is even less bound than sodium. So sodium, yes, sodium less bound than lithium. Potassium will be even less, a little bit less bound than sodium by a small amount. Will be a little bit less than 5. And then it becomes really already, much more complicated, and you do some structure. So you can see in the book. So you come to krypton. So there are many more elements. You start to feel. You will see more fluctuations because of feeling different orbitals. And you get to krypton. Krypton has something like hydrogen. as deeply bound as without that. And so on and so forth. So so it goes down to cesium. Cesium, I think, will be the less bound of all about. Then it's less clear. So then it goes less known, because you not always can measure that simply some different elements. So not all elements are known here on this curve, but general picture you can understand. Yeah.
What is cesium?
Yeah, that's cesium. Yeah.
SCS.
SCS. Huh? It's 133.
Oh.
So this number of cesium is 133.
There is 137, right?
In cesium,
Yes.
I do not know all isotopes.
In the laboratory.
In your laboratory, sure, the stable isotope.
The gamma varied and the 137. Yes, 127.
I'm sure you don't mix it with rubidium, because rubidium they have 87 and 95. I'm not sure. So I have different isotopes. I don't remember anybody working with 137. Everybody works with 900, 133. Probably you do. Yeah, I don't know. So there are several isotopes, but so 133 is not the Z number, right? So Z number is always the same. Z number is the number of protons. So once you go to a certain, so 133 is the atomic number, not the. So it's not the atomic number; it's the mass of your mass number, right? So it's not the Z. So this is why I don't mention this number, because this number is that. And for cesium, it's not 133. It's so about half of that, right? Should be something like a 76, something. This which more relevant number. I don't remember it. So it's not exactly the same number of protons and neutrons. It can be different.
That's stable situation. Cesium is stable or not stable?
Well, you say that you work with cesium.
Yes, it's if you radiate it, you get photons.
We will talk about that.
ionize it.
We will talk about that when I'm back. So the next lecture we will start to work on the interaction between the atoms and the electromagnetic wave.
Yes,
So that will answer your question. It's nothing to do with stability. It's just interaction with light. Or interaction with the excitation of atoms. So we will talk about that. Okay, so I think that I will stop here. So I will probably tell you a bit more when I'm back on the many electron atoms. But essentially, we will start to work on interaction between atoms and electromagnetic radiation. See how it works. I'm not here, so remind you, I'm not here next week, neither 2 weeks after the next week after that. So Rui will tell you a little bit about different systems. So he will give you a bit longer tutation than usual. Well, usual, he was only one time here. So now he will give let's say about 2, maybe 3 tutations. Probably we'll meet only once, so next week probably. So I'll check with Rui just again, and then you will have another free week. Just use these hours in order to finish homeworks, because once I return, I put the next homework on the web. You're ready to solve it already. Yeah.
Can we get the date of the final home exam so we can prepare to set the date? Is there any way to figure it out before the semester's end?
So the final exam, for example, one of the questions of the homework that you are doing now was once in the exam.
No, and what's the date? When
What's the date? Yeah. So okay. Tell me what do you want. Just try to find some day that will be convenient for you. I suppose that it will be nice. It will be probably more easier to find a day that will be toward the end of the period, the exam period. That will be easier, I think, to find. But try to connect to each other. Try to come next time together and ask. Again. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we are. I don't know how many people will at the end take the final exam. I have no idea. Usually the course was about that, what we have now, 10 people. 10 people was sort of, created a WhatsApp account, and they made a simple arrangement and found at the end a certain date. That was sort of an easy task. This year there was sort of 30 people that was inscribed on the course, but I don't see them. So they sort of evaporated, and probably they will be evaporated also on the final exam. So then that will be easy only for me, for you, and for those of you who will stay till the end, until the end. Okay, so let's try to find the date. I don't have any preferences, so whatever you tell me, I will be ready for that. Okay.